All right, welcome to today's Explainer. Get ready because we're diving into what is literally considered the holy grail of human engineering. For over 60 years, brilliant minds have been chasing this dream that, honestly, sounds a bit like magic, producing virtually unlimited, completely clean power. But as we're going to see today, the science has officially shifted from theoretical physics into a high-stakes, billion-dollar race that is happening right now.
Think about this. What if we could power the world using a literal glass of water? If you've seen an Iron Man movie, you know Tony Stark uses that glowing, compact arc reactor in his chest to make limitless, clean energy. Sounds like pure science fiction, right? Well, what if I told you we're currently building machines that do exactly that? And they run on fuel that's abundantly available right here on Earth, like isotopes found in a simple glass of seawater and traces of lithium.
Okay, let's get right into it. Part 1. A star on Earth. Fission versus fusion. To understand how this is actually possible, we've got to look at the fundamental physics. We are, quite literally, learning how to build a star on Earth. And this perfectly illustrates the difference. Today's nuclear power relies on fission. That involves taking a heavy, unstable atom, like uranium, and splitting it apart to release energy. But fusion, that is the exact opposite. It's the exact same process that powers our sun. Under extreme pressure and heat, light atoms, specifically hydrogen isotopes, are smashed together to form a larger atom, which releases just a truly tremendous amount of energy in the process. The practical differences between these two reactions are, well, night and day. Because fission splits heavy elements, it creates long-lived, highly radioactive waste and brings that inherent risk of a runaway chain reaction, a meltdown. Fusion is entirely different. It joins light atoms together. Its primary byproduct is helium. Yeah, the exact same inert, non-toxic gas we put in party balloons and actually desperately need for things like MRI machines. Even better, fusion is inherently safe. It's so unbelievably difficult to maintain the exact conditions needed for fusion that if literally any disturbance occurs, the plasma just cools in seconds and the reaction simply stops. A Fukushima-style accident is physically impossible in a fusion device.
So, the crucial point here is that fusion solves almost every single problem associated with modern energy production. It produces zero carbon emissions. There's no long-lived radioactive waste. There are no intermittency issues like we get when the wind stops blowing or the sun goes down. The fuel is virtually infinite, using deuterium extracted from seawater and tritium bred from lithium. And the energy density? It's staggering. To put it into perspective, just 1 single gram of fusion fuel generates the equivalent energy of 42,000 kilograms of coal. With global energy demands absolutely skyrocketing, especially with the rise of massive AI data centers, this is the ultimate baseload solution.
Let's move on to Part 2, Containing the Plasma, Engineering the Sun's Conditions.
Now, the sun relies on its massive gravity to crush atoms together. But here on Earth, we have to engineer those conditions ourselves. Step 1 is creating plasma, which is the fourth state of matter. When you take gases, specifically those heavy hydrogen isotopes, deuterium and tritium, and suspend them in a vacuum, you subject them to extreme heat. The heat is so intense that electrons are completely stripped away from their atoms. What you're left with is basically a soup of freely moving, positively charged nuclei. But since positive charges naturally repel each other, we have to force them to violently collide.
To overcome that natural repulsion, we have to heat this plasma to staggering temperatures. We're talking way hotter than the core of the sun itself. First, we use ohmic heating. By inducing an electrical current through the plasma, the ions accelerate and collide, creating resistance and heat. It's actually a lot like how the coils glow in your electric space heater at home. Second, we use neutral beam injection, shooting incredibly fast-moving neutral atoms straight into the plasma to ramp up the kinetic energy. Finally, we blast the whole thing with specific radio frequencies that perfectly match the natural vibration of the plasma atoms. This pushes the temperature all the way up to 100 million degrees Celsius.
But here's the catch. You can't just put 100 million degree plasma in a metal box. It would melt instantly. So engineers use two main approaches. The first is magnetic confinement, used in these donut-shaped machines called Tokamaks. They use massive superconducting magnets to trap the plasma mid-air in a magnetic field, so it never actually touches the walls. The second approach is inertial confinement. Instead of a continuous magnetic field, this method uses incredibly precise, high-energy lasers or electromagnetic pulses to rapidly compress a tiny pellet of fusion fuel, triggering a pulsed reaction.
All right, let's dive into Part 3, Historic Scientific Breakthroughs, the Inflection Point. For decades, the running joke was always, fusion is 20 years away and always will be. Well, not anymore. We have officially hit an inflection point of historic, back-to-back scientific breakthroughs. In December 2022, the U.S. National Ignition Facility made history by achieving fusion ignition. That means they got more energy out of the reaction than the lasers put in, but they definitely didn't stop there. By April 2025, they delivered a staggering 8.6 megajoules of fusion energy output. That is over 4 times the energy of the lasers used to drive it. They proved, once and for all, that ignition is not a fluke, it is a repeatable process. Meanwhile, over in the private sector, a company named Helion Energy achieved a massive milestone with their Polaris prototype. They became the first private machine to demonstrate measurable deuterium-tritium fusion, hitting plasma temperatures of 150 million degrees Celsius. That completely smashes the 100 million degree threshold required for a commercially relevant machine.
And when it comes to actually holding that plasma steady, China's East reactor set a world record by sustaining a stable plasma at over 100 million degrees for 1,056 seconds. That's nearly 18 minutes of sustained artificial sun. So you see, these aren't just laboratory curiosities anymore. These are the literal foundations for functioning power plants.
Which brings us to part 4, the billion-dollar race, the private sector ecosystem. Because the fundamental physics have finally been proven, the focus has completely shifted. We've transitioned from a slow government lab research phase into an absolute frantic sprint. By the end of 2025, total private investment in fusion hit a massive $10.6 billion, spread across 53 different companies globally. And this huge surge of capital? It's being driven by a very specific, very modern need, the massive, unprecedented power requirements of artificial intelligence. What's truly fascinating here is the sheer caliber of the players involved. Just look at Commonwealth Fusion Systems, building a tokamak with roughly $3 billion in backing from heavy hitters like Google and Bill Gates. You've got Helion Energy, backed by Microsoft and Sam Altman. TAE Technologies has Chevron and Google in their corner, and Pacific Fusion just raised the largest Series A in fusion history. We aren't just seeing standard venture capital, we're seeing the biggest energy and tech giants in the world placing massive bets on these distinct technological pathways. And they aren't just handing over research money either. These tech giants need clean, reliable baseload power to run their AI data centers right now, and honestly, solar and wind alone just can't cut it. Companies like Microsoft and Google are actually signing binding power purchase agreements for fusion energy today. They are already buying the electricity that these plants haven't even generated yet. The AI boom is acting as a massive accelerant for fusion commercialization.
So let's map this out. Part 5. Roadmap to the 2030s, from lab to grid.
So when does this sci-fi dream actually turn on the lights in our homes? Well, the timeline is moving incredibly fast. In 2026, Commonwealth Fusion Systems' Spark reactor begins operations, and TAE plans their Copernicus construction. By 2027, CFS is targeting their first net energy plasma. In 2028, Helion is literally scheduled to start delivering 50 megawatts of power directly to Microsoft. Now, while massive international collaborative projects like Europe's ITER have faced delays and are looking at 2034 for research operations, the nimble private sector is confidently projecting that the first commercial plants will connect to the grid in the early 2030s. This crazy accelerated timeline is really only possible because of parallel breakthroughs in other fields. For instance, we now have high-temperature superconducting magnets that are 13 times stronger than a standard MRI, enabling much smaller, far more efficient reactors. We're using AI like Google DeepMind's Tokamaks to run millions of virtual plasma simulations before a reactor is even switched on. And digital twin infrastructure from companies like NVIDIA is managing the millions of components required to build these machines. We are literally compressing decades of trial and error into mere weeks.
It's absolutely amazing to look at this powerful statement from Dr. Kim Boudil, the director of the Lawrence Livermore National Laboratory. She said, "The pursuit of fusion ignition in the laboratory is one of the most significant scientific challenges ever tackled by humanity, and achieving it is a triumph of science, engineering, and most of all, people." I think that really highlights the incredible, multi-generational dedication of scientists over the last 60 years that has finally brought us to the threshold of success.
Which brings us to the ultimate question. The physics is proven, the capital is flowing, the timelines are set. As our global demands for energy skyrocket alongside the AI revolution, are we finally witnessing the dawn of an era where humanity is powered by the very same process that lights up the stars? It certainly looks like the era of infinite, clean power is no longer science fiction. It is quite literally just over the horizon. Thanks for joining me on this explainer, and keep looking to the future.